Matrix is a set of numbers, and in OpenGL matrices are called column primary. This actually means that the first column of the matrix, or the first 4 elements in the array that represents the matrix in computer memory, must provide the first column of the matrix, followed by the second column, followed by the next column, and so forth. So this would be an example of a textbook representation. But when it gets to specify this matrix to give it to OpenGL, the storage has to be internally column primary. Trigonometry works very well in a single plane or 2D space. In 3D space, we need more linear algebra, and it involves computations with matrices and vectors. In physics, for example, when we try to design the physics engine for a 3D game, we start using more calculus. Matrix can move a vertex, technically speaking, translate a vertex in space. It can rotate vertices, and it can also scale a vertex. So of course, if we have a system of coordinates, right, so we have this Cartesian system of coordinates, and we have a vertex located somewhere here, so we can move it in a certain direction right here, so we can move it to a new location. Then we can try to rotate the vertex as an example, another transformation. So for instance, we want to rotate it around the y-axis. So then the rotation would proceed like this, right? So this would be the new position of our vertex. And then if we want to scale the vertex, it's basically will be calculating its distance from the origin of the system of coordinates and moving it somewhere in this direction. So this could be the final position of the vertex. So you see how these transformations could be combined together in matrices, allow us to both apply and accumulate desired transformations. Of course, GLM library can handle a lot of this stuff, but we need to learn a little bit about matrix math to understand how we can apply it in modeling and animation. One possible operation is matrix by vector multiplication. So we can multiply matrix by a vector, and it yields new vector. So the result of this multiplication is a new vector. And we can also multiply matrix by a matrix. In that case, we'll get a matrix result. So matrix by vector multiplication is actually a combination of addition and multiplications. So basically, if we have this example right here with A, B, C, D, E, F, and G, H, I, and X, Y, Z vector, so this is our matrix, then the new X component of the resulting vector will be A multiplied by X, B multiplied by Y, and C multiplied by Z, as you can see in these formulas. Likewise, when we start working with the Y component of the resulting vector, we multiply D by X, and then E by Y, and F by Z, production of new components of the resulting vector. So this is an example of matrix by vector multiplication, and here what we do is that we take the first column multiplied by the components of the vector. So 1 times 2 plus 0 times whatever, 2 times 1 plus 0 times whatever, so the outcome is 2 plus 2, and so we get from this combination here we get the result 4. Right. Same thing applies to the next column. 0 times 2, 3 times 5, 0 times 1, and 4 times 8. Sum together becomes 47, and then each row of the matrix results in the similar multiplication and addition, and we get our resulting components. So this is another step-by-step example. So multiplying a 3D space point location, which can be represented by a vector, so multiplying it by a matrix could result in transforming the location of this point to a new place. And here we have an example of a 4x4 matrix which encapsulates a rotation matrix around the z-axis. In fact, this is rotation by 90 degrees. So because we need this kind of matrix to perform this rotation, that's one of the reasons why we have to represent the xyz position by a 4-component vector and not 3-component vector, because this would be difficult to use with matrices. And this is the same example, but now step by step we're just filling in the question marks, which will result in a new vector right here. So basically what it comes down to is that when we take the vector described by this set of coordinates 1, 0, 0, this of course is the x, the normal x vector, and then we want to rotate it around the z-coordinate. A positive angle 90 degree here will rotate our vector counterclockwise in this direction. Okay, so this is the y coordinate, this is the z coordinate, and this is the x coordinate, and this is our original vector. So it's basically x is 1, y is 0, and z is 0. So it's this vector, and we're trying to rotate it. So of course 90 degree rotation should give us a normal vector in the direction of axis y. So if you do the necessary computations, of course cosine of 90 degree is 0 and sine of 90 degree is 1. So occasionally we need to apply a sine and continue multiplying every row in the matrix by the column specified by our vector and just filling in individual outcomes. So here we go. This is the resulting vector, and you can see that this is x is 0, y is 1, and z is 0. So this is our normal vector in the direction of the y-axis. A little bit later on in this series we will try to construct matrices like this and apply transformations to move our vertices in space using matrix by vector multiplication.